Okay, now the recording is on. We can go ahead with today's helping session. So, hi everyone. Thank you very much for joining today's session. Uh, I am Prerak. My full name is Prerak, and I will be helping you guys in this course. So, you can ask me any question if you have. Um, if you find any difficulty solving assignment, if you find difficulty understanding any concept, you guys can ask me in this session. And as you might already know, I will be taking these online sessions uh, regularly. Uh, so my session timing will be Monday, 7 to 9 o'clock. Okay, so it will be a 2 hour session. And I will be have some material prepared with me. I will be discussing some questions with you. Okay. Uh, and other than that, if you have any question or any difficulty understanding any question, you can either type in the chat box. I will be looking at your chats, or you can unmute yourself or and ask question in between. Okay, so I hope I'm audible to all of you, those who join later. Uh, and if I'm not audible and my video is like I'm speaking something and you are not able to hear what I'm saying, you can always raise your hand, or you can always type in the chat box. Okay, so just feel comfortable asking any question in between. So this will be an more or less informal session with you guys. Um, and if you find any difficulty understanding my language, you can also interrupt me in between. So I will try to be as simple. I will try to speak as simply as possible. And uh, yes, so anything you guys wanna ask me before we start? Okay, so so I am Prerak, and I will be helping you in these regular sessions. And I'm gonna help you in this basic real analysis course, which is offered by Professor I. Rana from IIT Bombay. This is an NPTEL course, and I will be conducting a 2 hour session with you guys. Okay, let's go ahead. Uh, yeah, so I'm from IISER Bhopal. Those who might know, IISER is an Indian institute. Uh, okay, and uh, yeah, I will be conducting these weekly discussion sessions with you, and this will be an 2 hour live discussion session. You can ask me your doubts. So you can ask your doubts. We can discuss concepts that are not clear. Any other question related to the course, you can ask me in this. Okay, and I will also be discussing some questions uh, related to the coursework. Okay, and recording of these sessions will be available on the YouTube channel, which is named as NPTEL TA Geometry of Vision Prerak Deep. So you can go to this channel. Okay, you can just type it in on YouTube search bar, and then you will be able to find my channel. And under this channel, I will create a playlist of this name, okay, of this course name, where you can find all these recordings. Okay, okay, now let's go ahead uh, with some questions. Okay, so first question we have is a set theoretic question. Um, so I will be discussing with very basic thing. assuming that you are not very much familiar with the union of sets and Cartesian product of sets. If you are familiar with, you can also answer in between when I ask some questions to you. Okay. So in this first question, you have given, you need to prove a set, a theoretic equality. Okay. So on the right hand side, you have given a Cartesian product of two sets. Okay. Where one set is A, uh, and another set is B union C. In B union C, B and C are also uh, sets. Okay. So ABC are sets. So that's what we know, that A, B, and C are sets. Okay. This is given to us. So B union C is what? Can anyone tell me what will be A union B? So how will the elements of A union B will look like? You guys can unmute yourself and you can directly answer the question. You don't need to type it in the chat box. Yes, I can hear some noise. Sorry. Your voice was not clear, whoever is speaking. Uh, Anyone else want to answer? What is A union B? A set that contains all elements of B and C. Very good, Hisham. So it's Hisham is actually correct. So A union B is basically set which contains all elements from B and all elements from C. So we know what is A union B. A union B is a set. Uh, so elements X, uh, such that X is either in B or X is either in C. I hope you all understand this mathematical notations. If you are having difficulty understanding these notations, you can stop me. You can raise your hand. There is an option in the Google Meet. You can raise your hand and you can stop me. I can answer you uh, here and there. Okay. So I hope it's clear. Uh, so A union B, yes, Arun. What's your doubt? Arun, it will be better if you can unmute yourself and ask. Otherwise, it will be difficult for me to know. Okay, so this A union B is a mathematical way where this X is an arbitrary element from B or either C, and this sign, which we call epsilon, it's called belongs to. Okay, it is a symbol for belongs to. So it says that this element X belongs to set B, and similarly, or X belongs to C means the symbol X belongs to the element X belongs to C. So this is a mathematical way of writing this A union B. Okay, so I hope it's clear to all of you. Now, if I consider the Cartesian product of any two sets. Okay, so let me start with some examples also, so it will be helpful for you to understand. So let's say if my B is this 1 comma 2 comma 3 and my C is 5 comma 8 comma 2. Okay, so so A and B are two subsets of integers. So what will be? So then what is B union C? Okay, so you just need to uh, put every element from each of the set to form this B union C. So it is a collection of all elements which is either in B or in C. So it will be 1, 2, 3, 5, 8. Okay, yeah. Okay, now let's move on to the cross product of two elements, because in the inequality we need to prove the cross product also. Okay, so uh, So I hope this is clear. A union B. This example is also very simple example that I've taken. Uh, Now let's move on to A cross B union C. Okay. So when you have an set theoretic equality, you need to prove. What do I mean by that? So you need to see, you need to observe that on the right hand side, you have a set. Okay. Because A cross B is also a set. A cross C is also a set. So what I'm saying is A cross B, it is a set. A cross C is again a set, and their union will again be a set. Okay. I'm using some basic properties of set theory, which say that Cartesian product of two sets is again a set, and union of sets is again a set. Okay. So this is a set. So basically on the right hand side, or which we call as RHS, right hand side, short form for that, is a set. As well as on the right hand side, we also have a set. Okay. Now you need to prove that these two sets are same. Okay. So what do we mean by that two sets are same? When do we say that two sets are same? We say two sets are same when elements, whatever element we have on one set is also contained in the on the other element on the set which is on the right hand side, and any other element on right hand side also contained in the left hand side set. Okay. So what did I say? I said that any element uh, x in so any element in LHS set which is A times B union C also contain in right hand side set which is A cross B union A cross C. Okay. So how do I write it mathematically? So mathematically I can just write this thing in a notational language which is similar to writing as any element x which is belongs to this set A cross B union C, uh, then x also belongs to A cross B union A cross C. Okay. So this gives me an inequality. It proves that the set on the left hand side contained inside the set on the right hand side. Okay. So it basically gives me an inequality. It doesn't give me an equality. Okay. So this proves that that the set on the left hand side contained inside the set on the right hand side. Okay. Now I want to prove the equality. I want to say that left hand side set and the right hand side set are equal. So I need to prove the inequality in the other way also. So this is so I also need to prove that A cross B, if I take the right hand side set, then it is contained inside the left hand side set. Okay. So now from these two equations, we can prove, we can say that both of the set on the right hand side and set on the left hand side are same. Okay. So I need to prove both of the things. Okay. So this I need to prove both of the statements. So first I'm proving that left hand set contained inside right hand set. This gives me one side containment, that left hand side set is contained inside right hand side set. Now I start with right hand side set and I prove that right hand side set also contained inside left hand side set, which forces that both sets needs to be equal. So this situation can only happen when both sets are equal. Okay, so yeah, so this is how we are gonna prove this particular um, set theoretic equation. Okay, is this clear? If you guys have any doubt, you can always raise your hand uh, during any point of time.
Hi Prerak, I have a one slightly off doubt. So what should be the book to follow for this course? Like, what do you suggest?
Okay, so there are multiple books. I will suggest there is Bartley Shevard name book, Basic Real Analysis. So it's basically a undergraduate level book. So usually the first year undergrad students uh, use this book to study this subject. And then there are other undergrad advanced books, which is a basic real analysis, oh sorry, which is mathematical analysis by Walter Rudin, which I won't suggest you to read at this moment. I will suggest you to read Bartley and Shevard. So you can just search it on Google. You will find its PDF online, uh, and you can buy it also if you are have nearby library or something. Okay, so yeah, assuming that you guys don't have any other question, yeah, and vice versa to prove this equality. Okay. Um, yes. So which also includes, and if I start with any x, let's say just vice versa, and otherwise. Okay, so now let's start with um, the formal writing part. So we need to prove. So now, how do we define? So let us just quickly recall what do we mean by Cartesian product of two sets. So if I have a set uh, A and a set B, okay. So let A and B be um, sets. So we define its Cartesian product A times B to be a tuple. Okay, so it's basically going to be a two tuple, where the first coordinate in this tuple will be coming from the first set, and the second coordinate in this tuple will be coming from the second set. Okay, so where A is in A and B is in B. Okay, so this is just this. So we call this to be the Cartesian product. Cartesian product of A and B. Okay. So now, for example, if you want to work with some real life example, so if I ask you to draw this, let's say if A is my interval 1 comma 0 comma 1 and B is another interval, let's say 1 comma 2. Okay. So my question will be then to you, uh, yeah, draw A cross B in R2 plane. Okay. So this will be my question to you. So can anyone uh, want to tell me how will this uh, Cartesian product of these two intervals will look like in R2?
You can draw a plane of like
Yes,
x-axis will be like 0 to 1 and the y-axis 1 to 2 and all the rectangle around it.
correct. So I hope everyone else also followed what he said. Uh, so this is my uh, these are my axes. This is x-axis and this is y-axis. And now I say that the first interval A is in the x-axis. So let's say this is my 0 comma 1 interval. Okay. Similarly, the 1 comma 2 interval, let's say it is in the y-axis. Okay. Now their product will look like nothing but this square which is formed by these two intervals. So this will be the, if I, so this will be the product. Okay. And now mathematically, if you want to write out the right, if you want to write down the elements of these products, so you can just follow the definition. Okay, you can directly follow the definition. So A cross B will be uh, element coming from A comma B, where A is in this interval 0 comma 1 and B is in 1 comma 2. Okay. So now my next question will be to you is this element which is 2 comma 1 belongs to A cross B? So you can verify from both things, from the
No.
figure also and from the diagram also. So it is not, it doesn't belongs to the Cartesian product because it doesn't, because 2 is not an element of A. Okay. So yeah, so this is a simple example uh, of cross product. I can also give you some simple discrete examples where you can just have discrete sets like we had in this case. So for example, if I do the cross product of B and C, so again instead of write, so you can explicitly write down the elements of B cross C. So elements will be 1 comma 5 and then 1 comma 8, 1 comma 2, 2 comma 5, and so on so forth. So the elements will be in total of 9. Okay, 3 cardinality of this and the times the cardinality of C. So these, so it will have only finitely many elements, and these will be the elements you will have. Okay, now let's move on to the question. So after recalling this Cartesian product, we can now finally, uh, yeah. So now we can finally prove the question. So if I go to the first part, so first part I'm styling. What do I mean by the first part? First part means the one side containment. Okay, first I will prove that left hand side set contained inside the right hand side set. Okay, so first I want to prove this. A cross B union C is contained inside A cross B union A cross C. Okay. So this will be the first uh, part of the proof. Yeah. So it is very direct. You just need to um, follow the definition of Cartesian product and the containment. Okay. Um so how will the elements of A cross B union C will look like? So the elements will typically look like uh, x comma y type form. Okay, so I will start with an element from this set, from this Cartesian product of two sets. Now my next task is to prove that this tuple belongs to the union of the either of the sets. So for that, what do I need to see here? So so in order to prove this containment, so I need to either have this thing, this that either this tuple belongs to A cross B or this tuple belongs to this. Okay. Um, so now we already know that the first tuple, first coordinate, already belongs to A. We already know that because we are starting with an element which is whose first tuple is from A. So we already know that part. Okay. So this is fine that X will always belongs to A. Now what about the second part? Now this Y will be an element of B union C. So we know that Y is an element of B union C. Now what does this mean? What is union? Union is, that means either Y is in B or Y is in C. Correct. Um, so let's say if bi is in B, so it basically breaks us into two cases. Let's say if bi is in B, then this x comma y as a tuple will belongs to A cross B. Okay. And if bi is in C, then this x comma y as a tuple belongs to x A cross C. Okay. So what we have proven is either this belongs to this or this belongs to this. Okay. In other words, x comma y belongs to this union. Okay. Which implies that we have started with an element of left hand set and we have proved that that element belongs to the set on the right. Okay. So it says that the set on the left contained inside the set on the right. Okay. So we have proved that A cross B union C is contained inside A cross B union A cross C. Okay. So um, this is the proof of the first part. Any one of you have any question in this? You can ask me. If not, then we can move ahead proving the next part. You can raise your hand in order to ask questions. You can unmute yourself and ask question. You can write on the chat box. Okay. So now let's prove the last part of this inequality. So last part is you need to prove that the right hand set contained inside the left hand set. Okay. So you need to prove that the right hand set is contained inside the left hand set. So they basically A cross B union A cross C is contained inside A cross B union C. This is what you need to prove. Okay. Uh, so we will start with an element which is x comma y, A cross B union A cross C. Okay. And then by definition of union, we know that either x comma y belongs to A cross B or x comma y belongs to A cross C. Okay. Now, in both of the cases, x will always belongs to A. Okay. This is what we can conclude from looking at both of the cases. And we can say that y can either belongs to B or to C, which is again equivalent to say that y belongs to B union C. Okay. So this implies that the tuple that we have started with is in the cross product, which looks like this. So in other words, we have proven the other part other containment, that the set on the right hand side is contained inside the set on the LHS. Okay, so there is also one more thing to notice. This argument of proving this site containment is actually the exactly opposite, exactly the reversed order uh, procedure which we followed in this case. Okay, so these statements are bi-equivalent. These are not just these statements are equivalent. These are not just implications. These are equivalent statements. So you can reverse the order of the argument in order to get the result. So this uh, so yeah, so you can get the containment from either this. So the argument of this part is completely reversed to the earlier part's argument. That's what I want to say. And now combinedly, this part, this first part, and this part, we will get the equality. Okay. So we, uh, yeah. So this is the first question that we wanted to discuss today. Any questions on this set theoretic equality?
No, sir.
Okay, thanks. Uh, I will wait for 20 seconds more and then we will move ahead to discuss next question. Um, okay, so let's see. So now the second question. Second question involves functions. Okay, and I don't know how much you are familiar with the functions. So I will go slow. If you want me to pace up, you can tell me that also. Okay. Uh, yeah. So the question is that consider any two non-empty set X and Y and subsets A, B of X, and you have a function from X to Y. Okay. So now you need to say whether this equality is either true or false. Okay. So
False, sir.
it's false. Okay. So let's say if it is true, then you need to give me an argument. Okay. And if it is false, you need to give me an example. Uh, example of X, Y, and F where uh, where this equality doesn't hold, where this equality, which is f of f of a intersection b, is not equal to f of a intersection f of b. Okay. So one of you have already said that it's false. Um, so in order to just make other also know why this will be false, I will start with assuming that it's true and try to prove it, uh, and then I will say that it's false, and I will produce an example to you. So for the learner who said that it's false, can you give me an example where it is not holding? If you know any, if you don't know, that is fine also. So any one of you know any example where this identity will be false? Basically, where this equality will not hold, this equality will be uh, false. If you don't know, that is also fine. I can give you an example. Uh, but now, if it is false, okay, now the next question is if it is false, then uh, can you say, so since we already know that it is false, okay, so let's just remove this first possibility that true, it's not true. Okay, so we start with the fact that it's false. Okay, but what can we say best out of this identity? What do I mean by that? So earlier I have explained that whenever we have identity offsets, so we try to prove it using the containment. Okay, we try to prove the left hand side set containing inside the right hand side set, and similarly right hand side set containing inside the left hand side set. Okay, uh, so first of all you need to observe that this is also a set. Okay, because we have given a function, so it is a intersection b is a set. This is a intersection b is a set. Function over it, function takes a set to a set. Okay, so a intersection b will be a subset of x. Okay, and it will take this subset to some subset of y. Okay, so this will be a subset of y. Similarly the right hand side, this is my right hand side, will be also an subset of y. Okay, similarly the right hand side will be also a subset of y. So again we have a set equality in some sense given, and you want to prove that whether it's true or not. Okay, so we have a set equality given. uh, Now what, we already know that it is false because one of you have already told us that it's false, so let's remove the possibility that it's true. Okay, now what can we say about this equality? Okay, what do I mean by that? That which side of containment will be possible? Okay, can we say this thing which I'm writing right now, that left hand side, that left hand side um, yeah, that the left hand side set is contained inside the right hand side set? Can we say that? Or can we say this, that or um, is contained inside this? Okay, so can we say either of the things? So first part is that uh, this thing. Okay, so first part is this, and the second part is this. So the my question is, uh, which one is, which one holds? A simple question. Which one of the following holds? Okay. Uh, so let me rephrase my question. Which one of the following holds? Okay. So I have changed my question into this part. Okay, because the equality doesn't hold. We already know that fact for something from one of our learner. So let's tweak this question into this part, that where will so if not equality, then what can hold? uh, so which side of containment will make sense and which side of containment will not be possible? Okay, so this will help us to produce example. That's what I'm trying to emphasis on. Okay, so
Hi, Prerak.
yeah.
Can you? I don't have the idea of like how function operates on sets. So can you? That will make this question
Okay,
clear. So
okay, thank you for pointing out that part. um, okay, so uh, function is basically an assignment from one set to another set. Okay, so in this case I'm having two sets, and third one is my function. So this is a function. So function is an assignment in some sense, that you say that, let's say this is my x and this is my y. Okay, so this is my set x and this is my set y, and I have a few elements over here. So these are my elements in this. Okay, I'm just drawing randomly. Okay, so I'm saying that this element of X will be assigned to some element Y in Y. Okay. And this element can also be assigned to some element. This element can also be assigned to some element. Now the only trick is that one element from X cannot be assigned to two elements in Y. Okay. So this element cannot be assigned to some different element as well in Y. So what I'm saying is one element from X needs to be assigned to a unique element in Y. So unique. So basically only one. So needs to be assigned to only one element in Y. Okay. So that's the only uh, speciality about the function. Okay. So I don't want to go into the relation part to define the functions because that will be tricky for you. I don't know your background as well. So I think this will make sense to you. So for example, uh, yeah. So if I have said 1, 2, 3, let's say, so this is one set, and I have set a 5, 3, 4, let's say. So uh, function, I'm defining a function 1 going to 5, 2 going to 3, and 3 going to 4. Okay. So this is my X, this is my Y. So I'm defining a function like this. Now, okay, okay, I'm just going to remove this part. Yeah, sorry, this part. Yeah. So yeah, so this is a well-defined function. So this is a function. But if I say that f1 also goes to 3, so this is not a function. Okay, so this assignment uh, needs to be done in such a way that each element of x goes to only one element in y. Okay, but now you may ask that will this be possible that I map all elements of x, let's say 1 also to 5, 2 also to 5, 3 also to 5. Yeah, this is possible because in this case you are not mapping, you are not assigning x two different values. Okay, you are assigning x only a single one value. Okay, you are assigning elements in x only a single value in y. Okay, you are not assigning two values in. Okay, but in y, different elements of x may have the same value. Okay, different elements of x may have the same value. In this case, this function will be called constant function because, as you might have guessed, is uh, because each element is going to the same value in y. Okay, so this is a constant function in some sense. So this is on the right hand side, which I have written that this is not possible. This is fine. This is fine. Okay. uh, yeah. So is this clear?
Yeah, it's clear. So according to that, I think that option two will be easier, and will be correct. I think
Hello.
what you wrote.
uh, is this clear to yeah.
Hello,
Saurabh?
your
Yes.
screen is not
Is this clear,
visible.
Saurabh? Saurabh, I can't hear you if you are saying something. So, okay. So I assume that you have understood this part. Now, let's get back to the question. Uh, so I'm gonna change this slide, or I'm gonna either remove this part. So if if Saurabh is fine, then I can do that. Okay. So now my question is, which one of the following holds? Okay. So because because you know that that equality of sets is false. So now what good can we have? So let us examine this first possibility. Okay. Am I audible now, Saurabh?
Yeah, yeah, you're audible.
For sure.
Okay, okay. So I was
Yeah,
asking
it
that
was
whether
clear. Yeah.
that definition was clear to you or not. Okay, okay, thanks. So now we move on to proving the we move on to examine the either of the cases. Okay, which side of equality inequality will hold, or which side of the inequality will not hold. So let us discuss this first possibility. In this first possibility, uh, you have given a left hand set and a right hand set. Okay, and now in these two sets, you need to prove that this containment holds. In other words, if you start with an element, okay, let's say A, um, in this left hand side set, okay, then will it belongs to, so we need to show that A also belongs to A intersection B. Okay, so this is what we want to show. Okay, how do we do that? So now so let us start with this part. So since A is in uh, the intersection of f of A and f of B, that means there is an element um, in A. Let's say call that element to be B in A, and an element in B as well, call that element to be C. Okay, because this intersection means that element needs to be in both of the sets at the same time. Okay, so yeah, so let's say there is an element in B in A and C in B such that f of B is equal to A and f of C is also equal to A. Okay, okay, so let me just go a bit slower. Okay, so just directly using the definition of intersection. So this definition of intersection says that A is an element of f of A and A is also an element of f of B. Okay, this is what intersection means. Okay, so now I use the definition of the function. Okay, so this is by definition of intersection. Okay, and now I use the definition of function. So when I say that an element belongs to the image of f of A, it means that there exists an element. uh, so let me just break it into two parts. Okay, so it says that there is B in A such that A is f of B. Similarly, there is B in B such that A is f of B. Okay, and both of the cases are happening because it's an AND situation. Okay. Oh, sorry, made a mistake over here. C. Okay, there is an element C in B such that this happens. Okay, but here is a big but over here, that this element B in A and this element C in B may not be same as B. Okay. Or B, uh, yeah, so they might not be same in, they might not be the same elements. They might not be the same elements. Sorry for that. Okay, so they might not be the same element. So you see the problem over here. If I start with this thing, so I'm getting an element in A whose image under F will be A, and I'm also getting an element of B whose image is again going to be A, but those two elements A and those two elements B and C may not be same element. Okay, so in other words, they may not lie. In other words, which implies that B or C uh, doesn't belongs to intersection of the sets, and hence it proves that A doesn't belongs to the image of the intersection. Okay, so I'm saying that there can be a possibility. Okay, so it's not exactly this thing. So it may be, it may be the case. Okay, maybe there can be some element. It may be this happens. Okay, so in such cases, we will not get the containment of left hand side into the right hand side. And now this hint us to an example. I can produce an example using this fact. Okay, so yeah, so let's see the example where this doesn't hold. So let's see this example where the identity of earlier identity doesn't hold. Earlier identity means this one. I meant this identity, okay, which where this identity doesn't hold, because I need to, if it's false, then I need to have some example to prove that this identity does not hold. Okay, so um, let's see an example. Okay, so if I take again, if I just start with A to be the interval 1 0 comma 1, and B to be an interval which is 2 comma 3. Okay, so um, yeah, so now we know that their intersection, and I define a function, and my bigger space X is R, my other space Y is also R. So here R is nothing but the real line. Okay, everything is real. Now I define, and these are my two subsets of X. Okay, now the second point is I define a function F from X to Y such that if I take an element A from X, I assign it to 5, okay, which is a constant function. So it is nothing but a constant function. So constant function. Okay, so it is a constant function. Now, uh, now, so is this function clear? So any element in so instead of writing x and y, I will write just r to r. So I'm taking a function from r to r where any real number is mapped to 5. So this is my function. Okay, now from the set, we know that A intersection B, it is empty because they don't have any intersection. The first set ends at 1, the second set starts at 2. So there is a gap of an interval 1 comma 2. So they are not intersecting. A and B are not intersecting, so it's empty. Okay, so now what will be the image set under F? It will again be empty. So empty image of empty set is again empty. Okay, so now what is F of A? F of A intersection F of B will be 5. Can anyone answer me this? Why this will be the case? So I'm asking why this thing, why this thing will be true, that intersection of f of a and intersection of f of a with f of b will be a singleton 5.
Because you are taking intersection of the both the five, right? If A
Correct,
also is
correct.
five, if B also is five.
Yeah, yes. So f of a is also singleton 5 because the range set of function. So we call this is called the domain part. Okay, where I'm taking from where I'm taking the values is, and where the values are landing are called the range part. Okay. Uh, so range of this function is always, so range of the function is 5. In this case, it's just a singleton 5. Okay. So f of a intersection f of b will be 5 only. So that's a correct guess. Um, and you can clearly see that f of a intersection f of b does not contain inside f of a intersection b, because a singleton set does not contain inside an empty set. Okay. But the other equality, okay, the other inequality, sorry, just a moment. Yeah. But the other inequality, which is another but other inequality, sorry, which is f of a intersection b contained inside f of a intersection b. So this is true in this case because empty set is always a subset of any given set. Okay, that is, this is convention. So empty set is always a subset of any given set. Okay, so f of a intersection b uh, is contained inside f of a intersection f of b in this case as well. Okay, so what we have concluded, so we have concluded a few things. So we have concluded that number one, that original uh, identity, which is f of a intersection b equal to f of a intersection f of b, this doesn't hold, does not hold. Okay, does not hold. Second thing we have noticed, that there might be a possibility, okay, of other inequality, okay, to hold. Okay, so maybe this other intersection, which is may sit inside or maybe contained inside this intersection. Okay, so now we have a strong intuition also to say that the intuition is coming from this example. Okay, the other side containment, and we have also proved that the statement is false, the original statement is false, and we have an example for that. Okay, so far so good, everyone is fine with this thing, with this example, why the statement is false, everything is clear. If any question, please ask, raise your hand. Okay, good. So now the other containment, I want to prove the other containment. Okay, so let's see, I will just again follows the basics, the definitions, and let's see how will it go. Okay, so yeah, so I will start with, let's say x, let's say x belongs to the left hand side, which is f of a intersection b. So what does this mean? This means, this implies that there is an element b, there is an element b in a intersection b, such that f of b is equal to x. Okay, And now, since this element is in A intersection B, now I use the definition of A intersection B. So it says that B is in A and also in C, sorry, also in B. Okay, now this implies that f of A, f of B, sorry, f of B will be in f of A and f of B will also be in f of B. Okay, these are just obvious deductions I'm doing. And now this fact, the fact which I have written on the right, that f of B is in this and this and this is nothing but the definition of the intersections. Okay, that means f of B is an element of f of B contained inside the intersection of f of A and f of B. And now what is f of B? F of B is nothing but x. So what I have proved is that f of A intersection B is contained inside f of A intersection f of. Okay, so here I ends the proof of this statement. Okay, so this is how mathematical argument works in general, and this is how we use definitions of uh, any symbol that we see in the mathematical uh, paper or document. Okay, so here I have nothing but I have used the simple argument of using, first of all, I use the definition of f, then I use the definition of intersection, then I use the definition of intersection, and then I deducted something by applying function on that, and that deduction was also obvious. And using that deduction, I see that this is similar to the saying that this is nothing but inside something which is inside the intersection. And now from that I have concluded what I wanted to conclude. So this is how mathematical arguments follows based on just axioms and definitions and properties of mathematical notions. Okay, so any question in this? So this is not a maybe statement. This is uh, a concrete statement. Okay. 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 So now you guys don't have anything else to discuss. So we move on to discussing the third question. This question might be a bit level up for you guys. I don't know is it, um, how much advanced this question will be. But anyway, I will go ahead and try to be I will try to give you the idea of this question. And I will not discuss the in detail this question because I have seen this question is also part of your assignment, current assignment, week one assignment. So also I will go through about the arguments. I will try to uh, emphasis on these terms, which is countable, the definition of algebraic numbers, okay, what is a polynomial, what is a root of a polynomial, and so on. Okay. So before proceeding, if you have any question related to this particular question, uh, you can ask me because I think you have already seen this question in your
Yeah, hi
assignments.
Pratik. This thing is we need to find
Yeah,
one-to-one correspondence between this natural numbers and this algebraic
correct,
number, right?
correct, correct,
So,
correct.
like, how to find that? Like, how can I find the one-to-one correspondence, right? How can I write down? So that is my question. Like, if you
Yes, yes,
can
yes,
just guide us that how you can find
yes,
the bijection, that will be.
yes, yes, yes. So the idea here is to use some results uh, on countable sets. Okay. So what are those results? First of all, let me just start with recalling the definition of countable. So as you have pointed out, that's a correct definition. So we say a set A is countable if there is a one-to-one, there is a one-to-one bijection, sorry, one-to-one correspondence, one-to-one correspondence onto the natural number set. Okay. So in other words, I have a bijection map from a map F from A to N or N to A, either way. Okay, so it's a bijection. So we say such set A to be countable. Okay. So for example, some examples of countable sets um, are these. Any finite set is countable. Okay. Number two is natural number set is countable because you can just map 1 to 1, 2 to 2, 3 to 3, and so on. So that will be in a bijection. Another example is integer set of all integers are countable. So how do you give an map from n to z? So this map from n to z, it's like uh, f of n. So we map evens, even natural numbers, even numbers to the positive integers, and odd numbers, or sorry, uh, odd numbers to the negative integers. Yes, something like that. So we map n by 2 if n is even, and minus so n minus 1, 1 by 2 if n is odd. So in this case, so when n is even, so basically if you start with 2, 4, 6, and so on, so you will map all the integers, positive integers, basically 1, 2, 3, 4, 5, 6, up to and so on. And when you start considering n to be odd, which is, let's say you say n equal to 1, so 1 it will be 0. Okay. And equal to 3, it will be minus 1, and equal to 5, it will be minus 2, and so on. So you will uh, so this part will map to all negative non-positive integers, and the upper part, the top part, will map to all positive integers. Okay. So in this way we will get the bijection from n to z. So these are three simplest example of countable sets you can think of. And then the other examples involves rational numbers. You can also, once you have the uh, countability, once you have proved that z is countable set, you can again prove that q is set of all rational numbers is countable. Okay. So this is, yeah, so let me write it with a different color. So this property number 4, sorry, this fact number 4, that q is countable. Okay. And then the another example is that product of countable sets. So this is also another property uh, of countable sets, which is product of countable set, uh, or countably many times product of countable set is again countable. Okay, it's not just a finite product of countable set, it is countably many times I'm performing the Cartesian product of countable set. Okay. So I will talk about in these uh, 2 points, basically this property number 4 and 5. Okay. So now 4 and 5 can be used to prove that any algebraic number is the set of all algebraic numbers is countable. Okay. So I will use property 4 and 5 to prove that set of all algebraic numbers is countable. Any question in this?
Hi, a general question
Yeah.
like I'm for engineering background, so let's say as far as I knew that you have to just list down the whatever set you want to see. If you can list it out, then it's countable. You can. Other than that, I
Yes.
don't know what is
Yes.
the method for like finding out n by two. What is that? Like, what is the general method of finding, or is just
No,
you have to
it's
come
not
up
the
with
general
some.
method. This is very specific to integers. Okay, because you want to list out integers in such a way that so basically I have defined a map. Okay, so this z n to z. Uh, yeah, so this is the definition, no? That from if you can define a bijection from the set to from n to that set, then it is called the countable set. Then the arranged set is called the countable set. So in this case, I'm saying that all the evens will go to so if so I'm defining this f of n to be this way that all the even goes to the positive integer. Basically, if I take, let's say, 1, so I think this will be easier, 3, 4, 5, 6, 7, 8, let's say. So what I'm doing this key, these, yeah, whatever is on the top will go to, will enlist the negative integer. So this will enlist 0, non-negative, non-positive integer. This will enlist the -1. This will enlist -2. This will enlist -3, and so on. And all the even numbers will enlist the remaining integers. Okay. So this is a way. So as you said, I'm listing out all the integers. Now this listing out uh, needs, so when you say you are listing out, so you are saying that basically what will come in the first place, what will come in the second place, what will come in the third place, and fourth and fifth and sixth. Correct, if I'm not wrong. So when you say that you are listing out something, you are particularly giving, you're particularly thinking of a function which is starting from n and going to your set which you want to list out. Okay. uh, are you with me?
Yes, yes, yeah.
Okay, so does that make sense? Because when you say you are listing out something, you are basically listing out, you are basically thinking of a function. In particular, you are saying that what will come in the first place, what will come in the second place, what will come in the third place, and fourth place, and fifth place, and so on. So this is nothing but an assignment. So you are assigning that first value will be assigned to something, second value will be assigned to something, third value will be assigned to something, fourth value will be assigned to something. So there is an assignment coming in the picture, and once you have the assignment, you have a function, as I have told you earlier. Because you are not giving first place, you are not saying that first place may have two objects sitting on it. Okay, you are just giving a single object sitting on first place. Correct. So in that way. So it is a well-defined function. So it is a function. It is bijection also because you are not leaving out any object from the arbitrary set which you want to enlist. And second, this is one-to-one correspondence. Every place is going to only single entity. Okay, so this is one-to-one correspondence as well. No two places are going to single element. Okay, what do I mean by that? So if I say that the first place, this is second place, so I'm not saying that on first place also goes to 3 and second place also goes to 3. I'm not saying that. This is one-to-one correspondence. So I'm saying that on first place, 0 will be sitting, second place 1 will be sitting, third place -1 will be sitting, and so on. So I'm basically giving an enlisting of z, and that enlisting will give us, mathematically it gives you is nothing but same as thinking of a function from natural number set to your arbitrary set which you want to enlist. If you can't enlist those objects in that arbitrary set, then it is not countable. If you can enlist and no element remain in the arbitrary set, then it is, and if you enlist in such a way that it is one-to-one bijection, correspondence, and so on, so it is countable set. So that's what I meant by that. Similarly, now the again question is, can you, again, now my question is, can you enlist uh, Q? So in other words, can you find out a map from N to Q, um, such that you say that on first place something what will sit, on the second place what will sit, third place what will sit? Can you give out such a map? So it will be difficult to answer immediately. Okay, you can't think of something uh, which comes directly. Okay, so we use some mathematical, so we use some mathematical relation to get there. Okay, so that's where the function, this function, notion of function comes useful. Okay, so that's why we don't use it in verbal manner like listing out or something, like ordering out or something. We don't use that. We say that it's a function. It makes uh, life easier to prove a lot of things. So that's where the mathematics comes in. So we introduce mathematics where we can simplify things. Okay. Okay. So I hope I'm clear to you. If I'm not, please stop me. Okay. So now let's come back to the fourth and fifth property. Okay. So now again you want, so the fourth property says that Q is countable set, and fifth is says that product of countable product of countable set is again countable. Okay. So let's first come back to Q. So again on Q we want to say that we want to give a assignment of natural numbers to elements of Q in one-to-one surjective manner. And how do we do that? So we already know that Z is in one-to-one correspondence with Q. Okay. So now in some sense we know that Z is in one-to-one correspondence with N, and if I can prove that Q is in one-to-one correspondence with Z, so I will be end up proving that N is in one-to-one correspondence with Q. Okay, because it will be then composition of two functions. So composition of two bijection function will again be bijection. Okay, so that can be an exercise that composition of two bijections is again again a bijection. Okay, and now you know the definition of rational. So rationals are defined to be um, fraction where uh, the numerator and denominator are coming from integers. So this can be is in Z, and Q is in Z minus 0 because we don't want denominator to be 0. So that's the definition of rationals. Now you want to give some uh, listing out of Q using these two variables. So uh, yeah, now you can list out Q using Z because you know that Z is already countable. So you can use that fact to list out elements of Q. Okay. And now once you can do that, you can directly say that because composition of function two bijection is again a bijection, and Q and and there is a bijection from Z to Q. So Q is also countable set. Okay. So I'm also leaving out that part where you can construct and bijection from Z to Q. So you can use this as a fact also that Q is countable set. Okay. And a hint can be like this. I can give you a hint uh, to prove that. So now you can think of Z cross Z. So before that, you need to prove that product of two countable set is again countable. Product of countable set. So what do we mean by product of countable sets? So let's say you have A and B, which are countable sets. Now you denote the elements of Now you consider the product A cross B. Okay. Now you arrange elements of A cross B in such a way that it is like A, because since A is countable, okay, so you can think of the elements will be like A, so you can think of A is elements being arranged in this fashion: A1, A2, A3, and so on. Similarly, elements of B can be think of being arranged in this fashion, in this way. So what do I mean by that? It is nothing but that on the first place A1 is sitting, on the second place A2 is sitting, and third place A3 is sitting. Similarly, on the first place B1 is sitting, second place B2 is sitting, B3 is sitting, and so on and so forth. So I'm using the same analogy to here, and I'm using them to. So basically, I can index out the elements of A. I can arrange the elements of A in a nice manner, okay, which will be useful to me. And now I can think of A cross B. Okay, so A cross B uh, can be A comma B1, A1. So I can just directly write A1 B1, A1 B2, and so on. Similarly, A2 B1, A2 B2, and so on. A3 B1, A3 B2, and so on. So this is an easier way to write down all these things. And now I need to I need to give an assignment. I need to give an function from natural numbers to this set. So how I will do? I will use this technique which is introduced by Cantor. Okay. So what he does, he basically strike out the elements from an arrow going from left to right. Okay, like this, like this. So you can see that on the first, it will hit the first element. So we will give this element to the first place, and then when the second arrow hits the second row, okay, so that element will be the second place, and then when it hits the next element in that diagonal, it will be list to the third element, and so on and so forth. So in this way you can keep on assigning. So in this way you can keep on. In this way you can keep on assigning places to the elements, okay, and you will end up getting an bijection from N to A cross B. Okay. Okay. Now once you have, so this is a proof for product of two countable sets is countable. So in this way you have proved that product of two countable set is countable. Similarly, you can prove product of countably many sets is again countable. Again, you can again have the uh, so you can again generalize either this argument, or you can keep that as a fact, or you can go back to the references to uh, see that. So we have proved that product of two countable set is uh, product of two countable. In this way, you can prove product of finite countable set also. Product of finite countable set is countable. Okay. And now you have Z, which is countable. Similarly, Z minus 0 is also countable. You can prove that because it is a subset of a countable set. So you can always uh, number them from, and you can always define a map from. So any subset of a countable set is again countable. That's another result. So yeah. So using that, now these two sets are countable. You can use, so which implies countables. These are countable sets. And now using these two sets, I can prove, now using the following the previous result, I can say that the product of countable sets, which is Z cross this, is also countable set. Okay, using the previous result. So this is also countable set. Now it's time to define a bijection from this set to Q. Okay, how can you define this bijection? You can start with point P comma Q, and this will go to P by Q. Okay, and this is a bijection because this is nothing but the definition of Q. So this is how you prove, and you have a bijection from here to N. Okay, so this come as a composition, this will be a bijection from this. This proves that Q is countable. Okay, so I've basically given you the proof of that Q is countable. Okay, now let's come back to the original problem. So we have proved these two problems. Okay, and countable product of countable product of countable set, we assume it to be the fact. Now let's come back to the original problem, which was that set of algebraic numbers. Uh, Set of algebraic numbers are also is countable. Okay. Cool. So how do we define the set of algebraic number? So let A be set of algebraic numbers. Okay. Then we need to find out an bijection f from N to A. To find f from N to A. Okay. So how do we do that? So we use this fact. Uh, we use the definition of algebraic numbers. I'm only going to use the definitions and the fact that I have proved. Uh, so algebraic number is nothing but, so we say that A is uh, algebraic number if that means there is a polynomial p x of some degree m um, in of some degree m, mm, such that p of A is 0. Okay, so yeah, so what we can do, we can basically classify algebraic numbers based on based on uh, of what polynomial they are root of. Okay, yeah, so in some sense we can find out divisions in these algebraic numbers. So degree 1 polynomial, basically roots of degree 1 polynomials plus not plus, basically union of roots of degree, two polynomials, and so on and so forth. Okay, so I have broken down this into these way. Okay, so each of which is a very big set. Okay, and we know that there are only that degrees uh, uh, are natural numbers, so you can only have positive degrees, positive integer degrees. Okay, degree zero polynomials will include the all the coefficients, but in that case only zero will be the solution, because for that the polynomial has to be have root, so it needs to be zero, so only zero constant polynomial, so that doesn't make sense because it doesn't have any. So we start with zero degree one polynomial and go on. Okay, so degree one polynomial will look like ax plus b, degree two polynomial will look like ax square plus bx plus c, and so on and so forth, where all these coefficients of the polynomials are coming from q. Okay, so we have some control, and we know that q is countable, and we know that these each of this set and sorry, and we know that uh, this division is also countable. Okay, we know that this division is also countable because degree 1, degree 2, and so on, so this is also countable. And now what is this? If I pick this set degree 1 polynomial, so I can see that the only variable which is changing, only the parameters which are changing is a and b. Okay, so this, if I consider this set of all degree 1 polynomials, so this is ax plus b, where a and b are in q. So it is nothing but same as thinking of it as Cartesian q, Cartesian q. So this will be an exercise for you. Okay, for you to figure out why these two sets are equal. Okay, and in this case you need to produce a bijection. You can't use the set theoretic argument that uh, this, because these two are different sets, so these two are same as a function. These two are bijective set. They are not uh, they are not basically they are not the same set, they are different set. Okay, so this is means that there is a function which gives us the bijection. So this and this, so these are two equivalent sets. And similarly degree 2 polynomials set will again be some q3, and as I increase degree n, then it will be same as qn. Okay, so q3 means product of q three times, and so on and so forth. Okay, so now we know that finite product of countable set is countable. So each of this set of q and q, these are all countables, and I'm taking the union of these countable sets countably many times. Okay, so another exercise will be for you. um, that countable, so this is first exercise. um, that countable union of countable set is countable. Okay, yeah, and now using these two facts, that each of this division set is countable, and union of countably many set is countable, so we prove the conclusion. But we prove that the set of all algebraic numbers is countable. But there is a gap. There are gaps in this proof which is filled with exercises. I have given you the overall idea how to prove this. So you need to figure out that I have proved that product of two countable set is countable, you need to figure out an argument why the product of finitely many countable set is again countable. Okay, so this will be the exercise again for you guys. And then uh, once you have that, now you need to prove that you need to give a bijective correspondence from q cross q to this set degree 1 polynomials. Similarly, for degree n polynomials there is a bijective correspondence with qn. Okay, you also need to give those. These are all exercises. It can be part of one exercise as well. When you just take when you don't take a specific degree, you just start with any degree n. Okay, so that will be one exercise. And then the third exercise is that countable union of countable set is countable. Okay, so this problem can be broken into these few steps, which involves that why q is countable, and then why finitely many product of countable set is countable, why countable union of countable set is countable, and why how can we think of the degree 1 polynomial set of all degree 1 polynomials as product of two rationals. Okay, okay, so uh, so this is the complete idea of the problem. Okay, and you need to fill in the details in order to make sense of the whole argument. Okay, so this completes the question number 3. uh, Now any question on this, anything which you haven't completely understood? Okay, um, good. So we have covered a lot of topics today. So we started with the product. We started with set theory, Cartesian product of two sets, and then then we discussed one problem which involves functions on set, and then we proved that some inequality or containment problem over there. Then we move on to some advanced problem which involves countability of sets and all. Uh, Okay, so now we further move on to discuss these concepts called sequences. So sequence has a very important role in real analysis. Okay, and sequence might and sequence are different from set. Okay, this is the first thing that I want to emphasis on. Sequences are different from set. So just quickly look at the definition of sequences. What is a sequence? Sequence is an assignment of elements. Okay, um, so is a function f from natural numbers to any real, or range can be anything, real, complex, or whatever you want, whatever is you sequence you want to lie in. So it is just nothing but where n is going to in R. Okay, so just a moment. Yes. Okay, so this will go to f of n. Okay, so instead of R I can have any other set also. So it's completely up to me what is my range. So I can take an arbitrary set x also, and I can define a sequence in that x. Now this looks very abstract to see. Now it will be great if we work with some examples, okay, to understand it better. Okay, so let's say my x. So I'm starting with a set on which I'm going to I'm going to define a sequence. So let's say my set is consist of only two elements, 1 2. Okay, so now can you give me a function or a sequence, um, yeah, can you give me a sequence uh, from where the elements are coming from X? Like this is a question from me to you. Can you think of a sequence? Okay, you just only need to think of where the what will be the first element. uh, you just only need to give me this correspondence. Okay, you can this could be any arbitrary correspondence. Anyone? Anything? Okay, so I will give you an example. uh, so this, if I say that all elements in n goes to single element 1 only. Okay, so 1 belongs to X, so it is a well-defined function. It's everything makes sense. And this sequence will look like 1, comma 1, and so on and so forth. So what I represent this sequence like this because at the first place 1, second place also 1, some ith place also 1 is sitting, and so on. So this is a sequence. I can also have a sequence which looks like this. Uh, okay, so there is also yeah, so there is also one sequence, um, 1, 2, 2, 1, 2, 1, and rest of the other entries are 1 only. So what do I mean by that? That at the first place 1 is sitting, second place 2 is sitting, third place 2 is sitting, fourth place 1 is sitting. So this arrangement of sitting position is very important in sequence. Okay. Um, yeah. So these arrangements of uh, elements sitting at which position is very important when you talk about sequences. Okay, so as I said, there are only two elements. Okay, I'm considering a sequence which is on two elements. Okay, 1 and 2. But as a sequence, I can construct infinitely many sequence which is on X. Okay, what do I mean by that? I can construct infinitely many sequence whose uh, elements, whose entries are coming from the set X. I can construct infinitely many sequences. Yeah. So this is set. This is a sequence. Sequence is just a function from natural numbers to that set. Okay. So it just only needs to be function. So you just specifying that this object is sitting on the first place, this object sitting on the second place, third place, fourth place, so on and so forth. Now you might ask how it is different from a countable set. In countable set also we have some type of ordering or listing or some type of objects listing out in a particular order. It is different because when we were talking about countable, we had a bijection. We need a one-to-one correspondence. The map needs to exhaust all the elements of X. Okay, and it also needs to be one to one. Okay, but in this case clearly you can see it is not one to one because constant sequence makes senses. Okay, constant sequence is a real thing. So constant sequence as a function, constant is not one to one function. Okay, because all the entries are going to a single entry in X. All the entries in n is going to single entry in X. So it is not one to one. So it is just a function. It is you just it is different from the countable part because countable you need a bijection function, which is one to one correspondence and surjective also. Okay, so I hope it is clear this sequence definition of sequence. Any question on this sequence?
No, Parik. Just
Okay,
move.
okay, good, um, good. So now we can move ahead to talk about convergent sequences. Okay, because the following question require this thing. So now once we are familiar with the sequences, now what do we mean by convergent sequence? We say a sequence you may notice a pattern in a sequence may seems to converge at some point. Okay, and sometimes they may not seems to converge at some point. Okay, so for example, in my last two examples, if you see the first sequence, okay, let's call that sequence some name, by some name, let's s1, and the second sequence by s2. So if you notice in the first sequence s1, you can guess where it will converge. It will converge to 1 because it is a constant sequence, each term is 1, so it will end up at 1. And what about the second sequence? Second sequence will also converge to 1 because after finitely many terms, after fifth term, rest of the entries are 1 only. Okay, so the tail of the sequence, which we call the tail of the sequence, which goes to infinity, uh, so that tail of the sequence is nothing but a constant sequence, which is 1. So s2 will also converge to 1. Okay, so this is how you can think of a convergent sequence. Okay, now what about this sequence? If I give you this sequence, this is a sequence S. Um, so how does this sequence looks like? So if I put n equal to 1, it will be 1. If I put n equal to 2, it is half. N equal to 3, 1 over 3, 1 over 4, and so on and so forth. So where do you see this sequence? Now my question is to you, is this sequence converging? Do you see a pattern and you think that this sequence will converge to something?
Yes, it will converge to 0
Okay, why do you say that it will converge to 0?
because it is decreasing and decreasing and decreasing. So
Correct.
at the infinite term, it will be 0, near to 0.
Yes, yes. Yes. So that's actually correct. So you can see a pattern over here and you can tell that uh, it will be converging to 0. You have correctly identified the pattern. Now how do we formalize this? Okay, so in mathematics we used to we there is a we try to formalize everything to make uh, to generalize the ideas. Okay, so we formalize this. Uh, just need to be with me. So yeah, before that, let me just stick to this particular example. Okay, so we have this real line. Okay, on this real line, this is my origin. Let's say. Okay, um, this is my origin, and let me try to plot these points. So this is 1, this is half, somewhere it will be 1 over 3, and then 1 over 4, and somewhere 1 over 5 over here, and then 1 over 6, and something, and it is going closer and closer and closer to 0. Okay, so if I take a near neighborhood means points near to 0. Okay, basically an open interval of some smaller radius. So if I take this smaller radius, I can see that all the other points except a few, all the other points are lying inside this neighborhood. Okay, so let's call the radius of this neighborhood to be epsilon. Okay, and I'm taking this to be my neighborhood. Now let's see what happens when I decrease the radius of the neighborhood. If I, let's say, take this shadowed part only. Okay, so I call that new epsilon to be epsilon naught. Now epsilon naught is smaller than epsilon, first thing. Second thing is, uh, second thing you can notice in this epsilon naught also, I'm leaving out a few terms, which is 1 over 4 or 1 over 5, let's say, but it is containing all the other terms from the sequence. Okay, so only, so at this, for epsilon naught also, only few terms, only a few terms, only a few finite terms are left out. Okay, only finite terms are left out. And now you go closer and closer. Okay, you start shrinking this neighborhood. So you go closer and closer. In other words, how you can say it mathematically, for any given epsilon. Okay, any given epsilon. Okay, for any given epsilon, this epsilon can be as small as you want, but it can be zero. You need to take some positive real, but you can go as closer, or you can go as bigger you want. Okay, you can either take this neighborhood, which is like this thing. Okay, so it is covering till this part. It is going till this part. Okay, and there here also it is going till this part, but it is not coming in the picture. So now in this bigger epsilon, which I will call the big epsilon, sorry, yeah, so in this bigger epsilon, let's call it epsilon 1. So in this bigger epsilon, you can see all the points in the all the points of the sequence is coming in this neighborhood. Okay, nothing is being left out. So, and if I go any larger than epsilon 1, uh, all the points will automatically be part of it. Okay, so the point that I want to say, because this is convergent, I have noticed a property from this, that if I take any neighborhood of epsilon radius centered at origin. Okay, origin in this case, because my sequence is converging to origin. Okay, if it is converging to any other point, let's say x naught, whatever point, then I will take neighborhood centered at that point of any radius epsilon. Okay, so any radius epsilon centered at origin, I take points, and then I try to see how many, if only finitely many sequence points are left out, then we are fine. So formally, mathematically, we write it as for any given epsilon, there exists some n, which in this case for epsilon, some n, such that um, xn minus x, which is the distance between xn and x, is smaller than epsilon for all n greater than n. Okay, so I think it is clear from the picture that I've drawn on the left what I meant by the convergent sequence. Then we say, then xn is a convergent sequence. Okay, and convergent sequence, and it converges to x. Okay, yeah. So this will be the definition that I will be using. Um, and now let's see this problem, question number 4. Okay, I don't have enough time to discuss this problem, but I will give you the idea of this problem. Okay, in this question you have given two sequences, and since this is also your assignment question, so I won't be discussing this in detail. So you have given two sequences, you know what sequences means. Okay, so uh, uh, so it is a map from n to rn, n to r, sorry. So it is a, so xn and yn are mapped from n to r and r, and we define other sequence to be mn, which is maximum of xn and yn, and mn, which is minimum of xn and yn. Okay, and now you say that this limit of both of the sequence exists. Now what can you say about the uh, limit of the sequences of minimum and maximum? Okay, so let me just, so mn is defined to be the maximum of xn and yn. Okay, and we assume that xn converges to x and yn converges to y as n tends to infinity. Okay, as n goes to higher values, is xn converges to x, yn converges to y. This is what we are assuming. Okay, so I will give you a pictorial argument for this maximum part. Minimum part you can think of by yourself, um, and I will not formally write the argument as well. Okay, so pictorially you can first of all think of dividing it into cases. So one of the cases can be uh, x. What is this? Sorry. Um, Case 1 when x is smaller than y. Okay, and case 2 can be y and x are same. Correct. So now in this first case, second case, because both are real numbers, you can find out the relation between them. So now let's draw the line. Okay, so now let's say this is x, let's say this is x, let's say this is y. Okay, now you know that xn and yn are uh, and y is greater than x, which is clear from the picture also. And now you know that xn converges to x, yn converges to y. So we can take, so in other words, if you take any small enough rate, any epsilon, and similarly any epsilon for y, you will be able to find out points of sequences after some finitely many points being sitting inside these neighborhoods. Okay, and you can always find out small enough neighborhoods centered at x and centered at y, which are disjoint from each other. Okay, so this is disjoint from this neighborhood of x and y. And now you can and it is clear also because these now these accents which will lie inside this small enough let's say epsilon naught radius neighborhood centered at x and some epsilon 1 radius of this thing, if we can take epsilon to be common also by choosing this thing, there is no problem in this, and yn sitting inside this neighborhood. Now you can clearly see these accents are smaller than yn. Okay, because they are sitting in a neighborhood which is far from it, and you can clearly see the differences for some common n. Okay, which satisfy for both of the epsilons, this epsilon also and this epsilon also. Okay, and now so the maximum after this n naught, the maximum sequence will only have yn terms. It will not be having xn terms. Okay, so the tail of the mn sequence in this case will converge to y. Okay, similarly you can again switch the role of x and y, thinking that y is smaller than x, and you can just repeat the similar argument. Now in case of when x and y are both are equal, so now in this case xn also converges to x, which is equal to y, yn also converges to x, which is equal to y, and this sequence mn will also converge to x, which is equal to y. Okay, so in other words, we will have three sequences converging to the same point x in this case, and to see this uh, yeah, so you again use the definition. You start with some given epsilon. Again, go back to the definition. You start with some epsilon and you try to find out n. So in this case, if you start with some epsilon, for xn you will get some n. Let's call that to be n naught. For yn sequence, you will also get some n. Let's call that to be n1. Okay. Now n1 and n naught, you can find out a maximum between n1 and n naught. Okay, which one is so some let's say n1 is larger, so you stick with that n1, and you say that for given an epsilon there exists n1 such that mn minus m will be smaller than this. So what I'm saying, for xn, for epsilon, in case of xn, this is xn case, this is yn case, you will get some n naught, and in this case you will get some n1 such that xn minus x is more than x epsilon for all n greater than n naught, y n minus y is smaller than epsilon for all n greater than n naught, sorry, n1. Now you think which one is larger, either this or this. Okay, so in either cases you pick the larger one, you pick the bigger one, and for mn sequence you just stick with that uh, ni, whatever is the bigger one. Okay, so and then you just need to say that mn minus x is smaller than epsilon because the limit will also converge to x. And this will be true because mn will either be xn or it will either be yn, because mn is nothing but the maximum of mn, xn, and yn. So it either be this thing, and for both of the cases, it is smaller than epsilon. Okay, so this will prove for the x equal to y case, and this as complete gives you a proof for maximum of xn and yn sequence is also convergent sequence, number one. And number two, you also know the limits also, and this is the particular argument. You can break into two cases and prove it. So I've given you the ideas only. I'm not discussed in very much detail, uh, but I think this idea conveys well. Uh, Similarly, you can also produce an argument for minimum case. Okay. Um, yes. So I hope I helped you in making this concept understand well. So I stop at this moment. We will meet next week, Monday, 7 o'clock, same Google Meet link, and we will discuss few more problems in this course. Thank you everyone for joining. So let me stop the recording.